Director of Research at AWS in charge of the AI labs. It's a pretty sizable organization at this point of scientists and engineers, and we build algorithms and machine learning models and other advanced solutions for AWS services. One of our biggest services is SageMaker, which is a platform for doing machine learning, which has been a very large ongoing collaborative effort of many people. On the slide here are some of the scientists, many engineers involved. I couldn't actually name all of them. I just want to give a shout out to Zohar Karnin, who's one of the best machine learning theorists you're likely to meet, and one of the brain behind a lot of the algorithms you're going to see. So before I start, I just want to set the stage. What is SageMaker in general? What is this AWS service? In general, we thought about, pretty much everybody thinks about machine learning as this process of exploring data, understanding what you want to do, training some machine learning models, hosting them, collecting data on how they behave in the wild, and then kind of going back and doing the same thing again and again and again. And our intuition, and which was by then validated, was that the quality of the solution, the machine learning solution you have in practice depends more on how often you go through this process, not necessarily how each separate component is done. So SageMaker is designed to actually let you go through this process fast and quickly and efficiently. So for the remainder of this talk, I'm going to talk only about the training side. So this is about taking data and training machine learning models. When we think about machine learning, training machine learning models, I think most of us still work on the single machine setting where you load some data on disk, you maybe load it into memory, you crunch it up on a pretty strong machine, maybe you have a GPU on that machine, and so you can do a lot, and then you get a model. I'm not trying to suggest that's not good. That's actually fantastic and sometimes exactly the right tool for the job. But oftentimes our customers at AWS say, hey, we just have more data. We want to deploy, we want to train on many machines. We want to use really complicated large models for which that model just doesn't work. And we have a lot of tools for it, but they just don't cut it. So anything from TensorFlow and MXNet and PyTorch and other things that help you do deep learning to things that deal more with traditional machine learning like SparkML and scikit-learn and others. And they basically say it doesn't work because we have really large machine learning problems, right? So we just collect billions of events a day. We try to host these things and they have 1,000 QPS and so on. And so this is just a sample. We have hundreds of customers who built either a part of the stack or the entire stack from scratch just because the tools out there were not sufficient. And so, and the things that they say they had trouble with is it's a large list of problems. Anything from stability and scalability, cost and time, accuracy, scale, data access patterns, competency of the team and how they build things, handoff between scientists and engineers, production readiness of the models, and so on. The list continues. And let me just dive into some of those difficulties just to understand kind of what people are struggling with. If you train a machine learning model on a single machine, it might take a few days or a few weeks if you have a lot of data. Maybe let's think about it as a week, plus minus. And you think to yourself, wait a second, I'm not training on my desktop, I'm training in the cloud. So for me, renting one machine for 100 hours costs exactly as much as taking 100 machines for 1 hour. So why don't I do that? I get exactly the same amount of horsepower. It costs exactly the same, but it finishes in an hour instead of 100 hours. So it's just better for me. So I would want that dot on the cloud to go horizontally to the left, right? So if I plot running time versus cost, because cost me is the same, right? Life is not so lucky because running a job on 100 machines is complicated, and there's communication and many other things kick in, and so you don't get perfect scaling. And so if you think about all the possible configuration you can set up, even assuming engineering is free and everything works and in the blue sky scenario, you don't get perfect scaling. And so you have this curve of trade-off between time and money. You have things that have to do with model selection. So or model tuning or hyperparameter tuning, right? So if you have a job that's running and it's expensive and slow and so on, that's bad enough. But you know that you have to run it tens, hundreds, thousands of times because you have to tune it, you have to change parameters, you have to tweak that, you have to fix it, and God forbid you have a bug, you have to repeat the whole thing, and then you get more data, you have to do the whole thing again. So the whole thing needs to be extremely scalable, extremely fast, and somehow you have to deal with this problem as well. Incremental training is a huge problem as well in terms of cost and time and ease of use. Many customers say, oh, we want to train on the last 30 days, say. And then they do that, and then the next day they have another day of data. And so now they train on the last 30 days, 29 of which they've already trained on. So all the I/O, all the storage, all the compute costs of that job, 29 out of 30 fraction of it, you've done just yesterday, right? And so that's a huge drain and source of misery. And lastly, every company has a notion of how important it is for their models or their machine learning to train on all the data, to be as accurate as possible, to have a bigger model, and so on. That estimate could be like one engineer for 2 weeks, or it could be a team of 20 engineers for a year, okay? But there's some limit on what they're willing to spend, because that's just what makes sense for their business. And so there's always, pretty much in every company, there's a cutoff. We say, okay, beyond this amount of data, beyond this complexity, we're just not willing to go because it just costs too much. And so there is the infeasible region of, we can't train on all the data, we can't train bigger models, we can deploy bigger models, and so on. Okay. So now I'm going to shift gears a little bit and tell you how we built our training infrastructure and algorithms that you can use on SageMaker such that they deal with all these problems. I'm not going to tell you how we got to making those decisions. Unfortunately, we don't have enough time for that. But I'm going to give you, just some ideas, and then I'm going to kind of point at how they solve these problems. So first of all, very opinionated, hard decisions we have to make is to say that all the algorithms in our system, all the training that we do is going to be one pass. Okay, it's all going to be streaming. So what does streaming algorithms mean? It means that you get a mini batch of data, and you have a state. That state is fixed. Think about it like a fixed size storage, a fixed size data structure, okay? And what the algorithm does is something conceptually very simple. They take a mini batch of data, they look at the state, they say, okay, I'm going to change it this way, I'm going to tweak, make this parameter a little bit higher, this a little bit lower, maybe update some counters and so on, and that's it. I'm going to, and then I'm going to forget I ever did anything. I'm going to take the next mini batch, I'm going to do the same thing, okay? That sounds terribly limiting, and I'm going to talk about why that is limiting in a minute. But if you can work in this model, you have huge advantages. So here are some of them. First of all, your memory is flat. Okay, no matter how much data you use, if it's a megabyte, a gigabyte, or a terabyte, your memory footprint is fixed. So your algorithm never breaks or never runs out of memory and never crashes just because you gave it too much data. It just never happens. It doesn't care. I mean, the first and the thousandth gigabyte conceptually do exactly the same thing. The second thing is in terms of ops. If you give an algorithm, a training algorithm of this kind, twice as much data, it's going to run twice as long and cost you twice as much. It's not going to go quadratically. It's not going to do something weird. It's not going to stall on you. It's just going to run linearly through the data. This is extremely important because if you have jobs running in production, you want to know that if the job yesterday took you 3 hours, the job today is going to take you 3 hours. Okay? Or if you give it more data, you know exactly how much longer it's going to take. Incremental training is solved immediately. So if you trained on 30 days of data, right, you get the next day now. Instead of forgetting the model from yesterday, you use the model in production, but you also take the state itself, everything that you saved along the way that lets you keep on training all the time. And you serialize it. And when the next day comes, you just deserialize it, keep training, and serialize again, right? Now, the algorithm doesn't even have to know that you stopped and started again. That's the interesting part. So the logic of the algorithm doesn't even know you ever stopped. because you serialize and deserialize the state, away from the logic of the algorithm. So the algorithm is unaware of the situation. If it just like woke up and said, oh, I get a mini batch of data, I update this, and then I fade out. Okay. And now you want to make, just in general, efficiency better. So of course, we all know about GPUs and other, well, mainly GPUs and better CPUs and communication and so on, which are all available on many different kinds of machines on AWS at this point. So we made sure that the algorithms that the algorithms and libraries we use can use GPUs and accelerate and make their computation more efficient. But that's not enough. We wanted to make sure we can run even faster, right? So we now need to distribute. And so what we can do behind the scenes, again, away from the logic of the algorithm, is we can shard the data to many different machines. And so because those algorithms are streaming, if you break the data in 3 parts, your algorithm is going to run exactly 3 times faster. Okay, it's just almost exactly. All right. Communication is the same and everything. If you do the sharding correctly, then you really should get almost exactly 3 times speed up. The only obvious problem with this setting is that the states of the different machines diverge. And so what we did is actually separated the state out and created a whole set of, like a whole service around it, such that all the machines see the same state. So they actually collaborate and actually train the same model. Okay, we should think I want to separate, by the way, the notion of the state and the model. Okay, the state is a superset of the model. You can get a model out of the state, but you not vice versa. Okay, so think about really the state as everything you need for training, and the model is everything you need for hosting, for scoring. So now we have this set of machines having getting a shard of the data, working with GPU-enabled logic and hardware, and all sharing the same state, training in the same time. And so what you get out of that is a huge acceleration and a huge boost in efficiency. And so we see just a drastic reduction in price and cost from the best alternatives that we can find. And finally, I kind of started hinting towards the fact that a lot of what we've done is actually abstracted this setting away from the logic of the algorithms, because we want to write many algorithms. We want to make them available to AWS customers, and we want to enable AWS customers to develop their own algorithms. And so we've abstracted as much as we can away from the container management underneath SageMaker to a fully optimized machine learning container with all the newest libraries and everything linked correctly and so on, which sounds like a trivial thing, but if you've ever tried to do that, that's kind of a pain. And then we have a thick SDK that controls all the communication and the serialization, all that stuff about the state and the shared parameter space and all that stuff. So you don't even have to know anything about it. And all you need to know as somebody who develops an algorithm is how you take a mini batch of data and look at it and change the state a little bit. And if you can fit your model into that setting, then everything else just works for you, which I think is kind of amazing. So I give you on the right kind of a half pseudocode, half actual code of something that just computes the median of a bunch of numbers. It's an example, but it actually works. So you interact with the state. I mean, you don't know about other machines and so on. This is, it's pretty much almost all the logic you would need for this algorithm to actually be deployed as a SageMaker algorithm. So. So the infeasible region that we talked about before now disappears because the burden of developing an algorithm is actually relatively small. The amount of code that needs to be reviewed and hardened for production is relatively small, and everything else is like super unified and already hardened for production. So when the scientist is done with developing an algorithm or a model, I mean, it just runs in production. You can just hand it off and it works. I want to spend about 2-3 minutes just hinting at the scientific difficulty of making complex algorithms fit in that logic that we talked about, the streaming setting. Okay. So let me talk again about the problem of finding the median. I gave you an example pseudocode for it. So if you think about, so when I think about the median, I think about, oh, you sort the numbers and take the middle element. But it actually, the median actually solves another optimization problem. It solves this optimization problem. So x, the minimizer for x is the median. The element that minimizes the sum of distances from all your data points. You can convince yourself that that's true if you want. It's a nice exercise. But you'll see that, so absolute value of x minus xi is a convex function in x. It looks like an absolute value, and it touches the x-axis at xi, so it kind of just move it to xi, and that's this function. And if you take a sum of those things, then it's a sum of convex functions, so it's a convex function itself. And in fact, it looks like that. So if I just took a bunch of random numbers between 0 and 1, and I look at the sum, it's that function over there, just this parabola-looking thing, and then like linear on the sides. And when you think about, so you think about minimizing functions, you think about gradient descent. When people think about machine learning, often these times, especially with younger folks, they equate in their head machine learning and deep learning is equated in backprop, and backprop is essentially gradient descent. So, you know, I think for many, at least practitioners, for them, machine learning and stochastic gradient descent are one and the same, almost. But I want to say that if you try to do stochastic gradient descent on this function, you get a pretty poor algorithm. Okay. First of all, you have to tune it, you have to play with it. It's very unstable. It converges extremely slowly. It's just a bad algorithm. Okay. Mind you, you can solve this algorithm. You can solve this problem exactly in linear time. Okay. Even worse, if your data has any shift, any time variant, any drift, any change, if your files are not like exactly perfectly shuffled, you get a statistical drift with anything that's stochastically training. Okay, and there's no way to fix that. There is absolutely no theory that's going to allow you to fix that. So you want to be able to create algorithms that are both streaming and don't have these instabilities and don't have these sensitivities to unshuffled data, because our data is not shuffled usually. I mean, there's nothing telling you that the first 31st day is exactly like the last 29. In fact, it's probably not, because otherwise, if it was, you shouldn't have retrained. You should have just kept the old model, right? So you kind of bet that the new data is different than the old data, and you still want to train. So we have techniques that come from sketching and online learning that actually allow you to do these updates in a way that reflects all of the history of all the data in a way that's either the same or better than what you would get had the data been shuffled. The algorithms are way more complicated, but they exist. Not for everything. This is still a wide open research area, and many problems are still unknown if we can solve them in this setting or not. But for most of the problems that you care about, the answer is we actually can, and we have. And so I want to tell you about some of the algorithms we actually already solved and put them in SageMaker for you to use today, if you want, on SageMaker. So if you go to SageMaker today, you'd find that you can create notebooks and start training jobs, host models as endpoints, and log the data and repeat. This is kind of the main console, the main landing page on the AWS console, the SageMaker console. And so I'm going to just kind of fly through the different algorithms that you have today and some of the performance boosts that we see already. So first of all, linear regression, linear classification, you know what those are. Something you might not know is that what you usually care about is 0-1 loss. So basically just the number of times, so the probability that you are wrong. That is an NP-hard problem. So we don't know how to solve this problem. We just don't. I mean, we know that we can't solve this problem, actually. So we use surrogate losses, and that requires a lot of tuning and a lot of experimentation by scientists, which is good because that means we have a job. So, but it still makes it hard. So in SageMaker, I'm not going to go exactly to what this slide means, but you really are able inside the logic of the algorithm to actually produce a lot of different models and a lot of different, kind of span a whole set of solutions that you're later able to combine and create more accurate solution from the state. And you get a huge acceleration and a boost in efficiency in terms of time versus speed as you scale and distribute these solutions. Factorization machines is another classification problem that sort of like one of the earliest like embedding type of results that was shown to be very successful. The best solution that we know for that was not scalable, was not distributed. And just by porting the logic and working on it in this setting, we were able to distribute almost exactly, perfectly. So you see going from 10 to 50 machines, we scale exactly horizontally. So this is, remember, we wanted the dot to go horizontally to the left. So here it does. It just goes almost exactly to the left. In k-means, you're trying to find a set of centers for the data, and you want to make sure the sum of square distances from points to those centers is not very large. Here we had to really reinvent the whole algorithm because nothing out there really works. So I don't know if you know how k-means algorithms work, if you know about Lloyd's or others. They don't look like gradient descent at all. So we really had to reinvent the entire thing. And when we do that, you see that when we compare to the other solution that we could have, and that other solution is Spark here, then we are much faster and more scalable than the Spark streaming k-means, which is the faster variant of k-means in Spark. And we're more accurate than the accurate version of Spark. So the Lloyd's, k-means plus Lloyd's, all right? And you see again, like roughly 10x boost in efficiency, so cost versus time, okay? And by the way, I don't know if you tried, I should probably advance, but it was, even to run the jobs that we were able to run, forget about efficiency, just even being able for the job to finish was not a trivial task in Spark often. PCA is in some sense very similar to k-means. Instead of k-points, you have a subspace of dimension k, and you still sum the distances squared. It's like a high-dimensional regression. Here, we get an insane boost just because GPUs are so great at matrix multiplication. So you're just like, just sharding data and everything ends up being extremely efficient. We have a time series forecasting algorithm called DeepAR, which is very popular. And training on large data sets that we couldn't even get R or other solutions to train on at all, you could do it in about an hour, and it costs you about $1 on AWS. So probably less than you're being paid sitting there waiting for it to finish. We have a topic modeling solution called neural topic modeling that I don't have time to talk about, but does very well in terms of perplexity and others, and scales very well. And we've just launched a few days ago Object2Vec. So this is a general framework for computing vector embeddings of objects. And so you have these encoders and decoder structures that are very common in deep learning today. And again, we see great performance even compared to very specific algorithms for text and images and so on. So, very exciting. I hope you go try it. We have new features coming out all the time. So this is, I should probably refresh it with more, newer launches, but this is in May. We launched pipe mode, so now your data doesn't even go through this. It goes through over network directly to the algorithm. Everything got better by 10, 20, 30% sometimes, so on. I'm running out of time, so I just want to show you how you launch a machine learning algorithm on SageMaker. So you may have many options. The point is that it's very simple. So if you launch a SageMaker notebook, you literally get a Jupyter notebook. I think most of you have seen one or work in one before. And so you just launch, say, PCA. You say how many instances you want and of what type and so on. You set the parameters, and then you just call fit, which is kind of like in scikit-learn. You just run. Okay, and we go off. We launch all the machines. We pipe it out. We do everything for you, and when it's done, we actually tear the whole thing down, so you don't have to pay for it anymore. And the cool thing about it, when you're done, you can do PCA predictor. So PCA.deploy. You see that box below? That would actually host your model. So that would take your model and put it behind an endpoint. And you can call the production team and say, hey, your new model is up. You can hit the endpoint. I mean, it's up. I mean, it's working. So you don't have to actually rely on anybody else. I know I'm beyond time, so I'll be done in about 30 seconds. You can call it from EMR, which is Amazon's hosted Spark solution, managed Spark, I should say. The cool thing is here, you really get a transformer, so you can just call it like you train any other transformer. And you can host solutions, again, directly and so on, which is very exciting. One of the most fun things about this is because we have this abstraction layer, we can, for example, train XGBoost as a Spark transformer, which is kind of awesome. I mean, without SageMaker, I wouldn't want to do it myself. It would be awful. If you have a quick hack on how to do it, let me know, because I think this is pretty hard to do. And of course, you can call it directly from command line from any EC2 instance. That's it, I think. Yeah. So that's it. Again, thank you. I want to just thank all my great collaborators and scientists and engineers who worked on this. And I hope you go try it.